Good morning. Welcome to our 4th annual Distinguished Alumni Award Assembly, which we are holding virtually for the 2nd year running. On behalf of the Board of Trustees, the Alumni Board, and the entire Alumni Association, I welcome you to this unique once-a-year celebration of our community and its ultimate product, our alumni. Each year, the Alumni Board receives names from faculty, staff, and alumni for consideration for this honor. The Alumni Board reviews the list and selects a single nominee in cooperation with the Board of Trustees. We are seeking alums whose work exemplifies the mission and values of the Overlake School and which is of service to humanity. Like our first 3 DAA honorees, this year's alum is doing work which is both inspiring and important, as you will hear momentarily. For students attending today, we hope this fills you with inspiration about what you can accomplish in your life. For faculty and staff, we hope that this affirms the hard work you do every day and every school year to help each owl become the best version of themselves. I would be remiss if I did not extend my thanks to the Alumni Board, the Board of Trustees, Head of School Matt Horvat, and all of you for making this possible. In our busy lives, from time to time, it is important to pause and remind ourselves what is truly important and to affirm the things we value and the reasons we work so hard. Please give a warm virtual welcome to Dr. Jeffrey Herron, class of 05, our 2021 Distinguished Alumni Award honoree. Dr. Herron.
Thank you for that very kind introduction. All right, so getting right into it. So I'm Jeffrey Herron. As Christian said, I attended Overlake from 1996 to 2005. And currently I'm a research professor at the University of Washington. What that means is I don't necessarily have to teach classes to large numbers of students. Instead, I focus entirely on grant-funded research and mentoring graduate students as they basically engage in research activities in my lab. Now, what does my lab do? Well, I work in the development of brain-computer interfaces, which basically to improve the treatment of people with neurological disorders like Parkinson's disease or essential tremor, as well as potentially, hopefully, help in the future people who suffer from terrible neurological injuries such as stroke or spinal cord injury. So let's dig a little bit into, first off, what is a brain-computer interface and what am I talking about? Brain-computer interfaces are fundamentally a device or system that interacts directly with the brain, our central nervous system. Functionality is kind of split into 2 different components: reading out information from the brain, sensing neural signals, and then there's writing in information, stimulating neurons to basically provide some sort of feedback that can be interpreted by the person that's receiving that information. Brain-computer interfaces have been, at this point, popularized widely in media. In pop culture, everything from books such as William Gibson's Neuromancer up to last year's release of Cyberpunk 2077. Brain-computer interfaces are often associated with a cyberpunk genre where these systems are basically fundamentally interacting with the brains and allowing unparalleled control over machines using someone's own brain. Now, in the real life, though, we're clearly not at the point where we can control arbitrary, device, live in a complete virtual reality through a brain-computer interface like in the Matrix. Instead, brain-computer interfaces are used widely in the medical space. First off, one example of brain-computer interface is a deep brain stimulator. These devices are implanted much like a cardiac pacemaker in the chest, and then instead of an electrode going into the heart, an electrode goes into the brain, into deep brain areas to stimulate these circuits in ways that basically different symptoms of neurological disorders are alleviated. People who have tremor no longer have to tremor. people who might have mood disorders. There's currently ongoing research into alleviating depression. Deep brain stimulation is one of the most widely invasive, as in it's something that is implanted in the body, brain-computer interfaces of today. Now that's a stimulation device, like so that's a writing in. An example of a reading out, I'm going to warn you, there's going to be a bit of a graphic image here, is the implantation of electrodes for seizure mapping. In patients who have chronic seizures, electrodes are implanted directly on top of the brain to monitor electrical activity across the entire brain to then hopefully determine where these seizures are being generated from. So a neurosurgeon can either implant a device that might stimulate or potentially go in and resect the tissue that's causing these debilitating illnesses. So this would be an example of a reading out type of brain-computer interface. Now, there's also non-invasive brain-computer interfaces. These are also widely used in the clinical and medical space. Electroencephalography, or EEG, is the using of electrodes on the skin of the surface of the skull. And these are, commonly used in the diagnosis of sleep disorders, but also something relatively straightforward to use in various research projects where we're trying to map areas of the brain because it doesn't require any type of surgery to use these sort of devices. And this is an example of, again, a reading out type system. And then there's also the use of large magnetic coils to drive induced currents within the brain called transcranial magnetic stimulation, TMS, which is used as one of a treatment form of depression. Now, all these systems I've talked about so far usually it's just you're seeing either a stimulation or a sensing functionality separately. There's been some really exciting demonstrations in the last decade showing where these systems can start being used as more bidirectional, as in systems that both sense and stimulate at the same time. And these are being used widely explored in establishing communication methods so that paralyzed patients might be able to control computers with their brain, or potentially have robotic arms assist in their daily living. Now, my research focus specifically in this wide area is I'm working currently on two major projects. One, on those deep brain stimulation systems I referred to, we're now making use of sensing from the brain to control the stimulation in this quote unquote bidirectional neural prosthetic. The other work I do, we've just been starting up at the University of Washington, is we've been starting to study how people can use brain-computer interfaces in a virtual environment to control or receive information from some sort of task presented in VR, such that we can learn more about how the brain works and processes information. But stepping back for a second, what's it like working in the field of brain-computer interfaces? And one of my main messages I want to get across today is it's really not the sort of work you can do by yourself, not least of in someone's garage. Instead, brain-computer interface is a multidisciplinary field with experts participating from a variety of different domains: engineering, science, medicine, and in the field of ethics. Team science is the way that this field moves forward. But even this is far too coarse of a way of breaking this down, because within any of those different fields, there are different domains of expertise that are required for these basically different projects. Everything from patient advocates to psychologists, neurosurgeons, and even when you start breaking this down into specific forms and functions of what individuals can hope to cover themselves, it starts to blossom into at this point, a poorly designed color-coded flower. But the point is clear, is that there's no one single path to working in the field of BCI. Instead, the most ambitious projects actually require large teams of people with a variety of different expertises working together. And so let these people coming from all these different paths potentially, well, let's use myself as a case study. How did I get here? And what I did is basically, after finishing up at Overlake in 2005, I went on to the University of British Columbia, where I got a degree in electrical engineering with a specific biomedical focus. And then I worked for several years in Microsoft's research hardware prototyping lab before going back to grad school. Now, grad school is something I didn't know a whole lot about when I was in high school. The only thing I understood when I was a high schooler at Overlake was I needed to go to college. I didn't really know a whole lot about what the different degrees meant, other than the fact that I was going to get a high school degree and then I was going to go on and get this thing called a bachelor's degree at university. I didn't really understand much like that. And fundamentally, universities are structured a lot like Overlake is, with a middle school and then an upper school. The middle school that everyone enters is the bachelor's program, but this on top of that is the graduate programs. And so what are these degrees beyond the bachelor's that you can get at universities in the upper school advanced courses, the master's degree and the doctorate of philosophy? Master's degrees take usually an extra 1 to 2 years. There's sometimes a requirement to teach, and they basically result often in higher pay in many jobs, specifically in technical professions, but across a variety of different professions as well. Master's degree often result in higher pay. So they're also something that often some professionals will take through night courses and stuff like that, such that they can then basically get it on the side whilst working full time. PhDs, or doctorates of philosophies, not only come with the really slick doctor title once you achieve it, but basically it's the fundamental requirement for teaching at a university, becoming a professor. It's also generally seen to be required for leading research in industry, working at companies, or in academia, the university system. But what do I mean by leading research? And this kind of gets into the question of why would someone get a PhD? Well, while I was working at Microsoft before coming back to grad school to get my PhD, my mentor told me a couple things. First, PhD isn't required to work on research projects. I was actually working on research projects with my bachelor's degree working in Microsoft. There's a multitude of roles that people can use that pushing forward technology and science, and great ideas can come from anywhere. PhDs instead are required to lead and manage research, overseeing the development of ideas into something that could be disseminable. That's the domain of the PhD, so to speak. The other thing you told me, and this was just something that I got a lot of, I got some value out of, is that PhDs aren't a mark of intelligence. Don't assume that someone has a PhD that they're smart. I could make a self-deprecating remark about myself at this point. Instead, what it really is a marker of is, in some ways, it's stubbornness. Not only is it hard pushing forward research, it's also a lot of extra school that isn't necessarily needed to have a successful career. But ultimately, it's a lot of ways it takes a certain degree of stubbornness to take a new idea and wrestle it to the ground, and to basically make it into something that you can then tell other people how to go about and push develop new technologies. I entered into undergraduate program, and then at the end of my undergraduate, in the last summer, I worked in a lab working alongside graduate students. And at this point, I was trying to figure out what I was going to be doing with my life. And graduate school was something at this point I'd learned about might be an option. While I was working in that lab that summer, I learned that basically this little flow chart that I put together showing the progress from high school to professordom is a little bit, it's not necessarily fully complete. Especially for myself as an engineer, there was graduate students I was working with who went off after working in undergrad and worked in industry at companies before coming back to their PhD programs. And I have to say, the students that I met that summer who had worked in industry were all incredibly impressive. They had really well-established technical skills. They were they were driven. They were there for a reason, because they had left ultimately a high-paying job to come back and get more school for some reason or another. So I decided I thought this sounded like a good idea. I wanted to go off and get work in industry too. And I ended up, as I previously mentioned, after I finished up my graduate degree, I ended up at Microsoft as a contractor. 2010, and people in the audience might understand that this was a great recession, so a contractor was about the best I could do. And then the following year, I applied to graduate school. I applied to 10 programs. I got rejected from all 10 of them. And fundamentally, the thing I want to talk about is that this was a failure of networking. Effectively, what I mean by that is that I basically, by submitting an application, I ended up being a good application in a pile of good applications. The schools who were receiving me didn't know who I was. The professors who I was potentially going to be working with, I was an unknown. applying to PhD programs is often actually a lot more similar to applying to a job, because you're committing to work in someone's lab doing research for them for 4 or more years. And so fundamentally, the problem was that I was cold calling. I was basically sending in applications without any backup. And so what I did the next year, I basically took a lesson, and I started volunteering at research projects at the University of Washington. Luckily, I could do that because I was local. I started working with professors in my spare time while holding down my full-time job at Microsoft. And then I also leveraged some of those industrial connections to basically arrange, at the time, a remote meeting with the head of the engineering at Stanford, at the East Electrical Engineering Department at Stanford. And that let me become known to those 2 schools. So the next year, when I again applied to the 10 programs, I got into University of Washington and Stanford. And then I chose to go to the University of Washington, and that might surprise some people. And I'll say one of the, when applying to grad schools, rankings, as many people kind of conceive of them at the high school level, like I myself did, matter a lot less at the graduate level. What's way more important at the graduate level programs is the specific expertises in the area you want to get your research, you do your research in. And I determined that University of Washington had a much stronger program in the neural engineering and neuroscience space than Stanford did. And that ultimately there was a lot of funding for research at the University of Washington, thanks to a big NSF grant. So I decided to go to the University of Washington, and then fast forward several years. I finished up my PhD. I wrote a thesis on some of the initial demonstrations of adaptive deep brain stimulation. So those bidirectional prosthetics that I still work on today, using sensing to drive a stimulator to hopefully treat people's tremor or movement disorders better. I wrote a thesis, I finished it, and then I went off to work at Medtronic for several years. And this is because I thought I wanted to go off and I wanted to lead industrial research. And I wanted to basically someday be a director of research at Medtronic. And this would have traditionally, this removes me from that traditional pathway towards professor, where I would have normally, quote unquote, gone on and worked as a postdoc in someone else's lab, and then started writing grants, and then become a professor at some other university. But as indicative by how I started off this program with the fact that I am a professor at University of Washington, one of the key lessons I want to also maybe drive home is that in this era of team-based science with multidisciplinary skills, sometimes those traditions are maybe a little overrated. The skills I gained in industry made me a very attractive hire to join a multidisciplinary team here at the University of Washington, developing these new neural systems and devices to treat neurological disorders. And so that's how I ended up in my current position after finishing up, basically getting out of what I wanted out of my time at Medtronic. So why am I telling you this big long story? Stepping back again. Basically, I'm just trying to relay a couple things here that I didn't necessarily know that might be helpful for any of you if you're pursuing a career in science or research engineering, or really, as I kind of indicated from my multicolored flower from earlier, even in the space of ethics or medicine, right? And what I will say is that in this multidisciplinary team-based world, the most important skills are not the scientific or statistical or experimental ones. They're the soft skills. It's the interpersonal skills. It's the ability to work as a team member, being resilient, and then also ultimately networking to basically both for new jobs, but also networking in order to identify your good collaborators, the people who will be on the team with you. These are the critical aspects of your career that are really will in many ways lead to success. The second thing is that, like I kind of indicated through my discussion about this winding path through university education programs and industry and then back again several times, there isn't really necessarily a specific single best path to any specific destination or career goal. This would have been good context for me as well. And also sometimes it's okay for your destinations or goal to change. What's really I found important is to try to keep doors open. And what I mean by that is, while I was working at Medtronic, I wanted to keep the door open to return to academia. So I worked really hard to convince my bosses there that I needed to continue to publish research papers while being a Medtronic employee. And that left the door open for me then to have an expanded set of publications that I could then justify my professor title when I went back. I basically worked extra in some ways to leave those doors open for myself. And then finally, I'm sure you've all heard this again and again, but one of the key things that everyone will always say about is that from Overlake is that the writing skills were useful. And I'm sorry that I'm going to fall into that trope along with the rest of them. And that's because specifically in a career in science, what's important isn't just the science you do, but being able to disseminate that. And also put in proposals for funding for your work. This is all fundamentally writing skills. And basically, it's more than in any other field. I spend more of my time writing nowadays than I do spend doing anything else. And really, that foundational approach in terms of writing is really, really helpful in a career in science. So wrapping it up, I want to kind of give a couple little shout outs to people who I think who were really important to me when I was a student, and I think are still around. First and foremost, Bill Johns and Sarah Fitzpatrick. The time doing technical theater at Overlake proved to me that I could be creative and technical at the same time, and those have been some of the most. I have some very strong, wonderful memories of spending time with you guys doing that technical theater. So thank you for all that. Sarah Gallagher and Bill Armstrong, thank you for teaching me. I know it took some effort. Everything I could do to basically be a good writer. I know that took real effort from you guys, and I'm always thankful for it. And then, of course, Gerald Bleicher and Lisa Orenstein, thank you again for all that you did to make science really something I could enjoy. And then I want to give a quick shout out to my new neighbor, Kara Wright, who I think is going to be a fabulous addition. I know is new at Overlake, and I think she's going to be a wonderful addition to the community. All right, with that, I'd like to open it up to questions. I think there's some time for some questions. Christian, I think I hand it over to you now.
Yes, so I'll toss a couple questions to you. First of all, Dr. Herron, thank you for cramming all that information into less than 30 minutes. That's a lot of really valuable stuff for our students and others to hear. Let me throw you a couple questions at you that came from our neurological science club. How has the field of neurological science, the surgery, the technology changed in your career? And how do you predict it might change for the next 5 to 10 years?
Yeah, I think one of the key things that I've been seeing is this drive from separate systems, clinical systems that would perform either sensing or stimulation functionality by themselves into basically the creation of more complicated systems that can basically synergistically leverage both aspects to have some greater outcome. And the main reason why in large part why that's been a major push of the last decade is that we finally have now devices that are recording in addition to stimulating and basically making that data available. And so the research tools front in this space has been blossoming into something that we can make use of in human grade research contexts, which is one area where basically there's always difficulty translating findings from preclinical or animal models into basically human type research where we know basically we can basically start to create new therapies and new outcomes, and that will actually hopefully be something generalizable across different domains. And I think that coupling of stimulation and sensing technologies in this bidirectional space is something that's only going to continue to grow and become more important as we get better computational models that will basically predict how and where we should be doing sensing and stimulation. And so this massive influx of data and the improvements of data science are coming together, I think, to enable a new generations of sensing and stimulation systems.
I would say, in a conversation you and I had a couple of years ago at your office, we were talking about how, for example, pacemakers are based on the deep understanding that our medical community and scientists have gained about the human heart in the last 100 years, certainly. And you had mentioned that the brain, we have a lot farther to go in the brain, partly because it's a more mysterious device than a heart in some ways, more electrical than mechanical. Can you talk a little bit about where you think we are now, if you compare our knowledge of the heart versus our knowledge of the brain, which I realize isn't really a fair question, give us some idea of what you think the extent of that knowledge is compared to what it's probably going to be eventually.
Yeah, I will say one thing that I've learned to be comfortable with in working in this field of neuroscience is very comfortable with the phrase, "I don't know." And that's fundamentally because we're dealing with like when I'm talking about these various therapies around the deep brain stimulator that alleviates Parkinson's disease. Everyone in the medical community goes, when you ask them how does it work, everyone will tell you the same 3 words: I don't know. There are hypotheses, of course, right? And the hypotheses are based on some of our preliminary kind of models or understandings, but they're all very basic and don't account for nearly the sort of variability anybody would really truly want. And so at this point, I'm sorry to say the brain is still a big, mysterious gray blob. As far as I'm concerned, it's responsible for a whole lot. And I think I look forward to seeing how our knowledge will grow. Am I going to make any predictions though? No. I'm not even going to be that adventurous, because at some point it's just going to be we're going to have to see and hopefully be pleasantly surprised, but also potentially disappointed that our knowledge of the brain isn't going to grow as fast as some of us want it to. So that's why I focus on interfacing,
right,
ultimately, so that we can then develop better systems to collect more data. Because I am passionate about learning more about the brain. That's what got me into this field. I have no capacity to basically predict very far ahead into, where we're going to be in the next 10 years from now.
I think on that note, we'll come to a pause here. Dr. Herron, thank you so much for taking time out of your very busy schedule to share a little bit of what you're doing and why, and for sharing your path. And thank you for the work you're doing on behalf of humanity, and many of us may benefit from that work now or in the future. And I hope you'll come and visit us on campus sometime in the near future. Thanks everyone for being here today, and we'll try to share this out for anybody who missed it in case not everybody was able to attend. Dr. Herron, thank you again.
Thank you very much. Have a good day, everybody.
Congratulations. Bye-bye.